Hi guys, Megan here from Orgo 2. I'm your classmate. I just wanted to make some comments and um, I don't know, ask for suggestions and kind of talk about what's happening with these intramolecular Diels Alder reactions because I don't really feel like that's something that's intuitive, something that is even natural to be able to understand. It's something you definitely have to work with and work for understanding, especially considering that our textbook offers nothing about intermolecular, at least from what I read. I quite possibly could have looked over something, but I didn't see anything on intermolecular or intramolecular. Inter is two, intra is within one. So intramolecular Diels Alder reactions. And this was on our exam, and it was a significant point value at 9 points, which I'm sure I missed because I simply ran out of time on the last 3 pages. I'm not ashamed to say that I really struggled with this past exam. So um, it's good to talk about those things. You have to talk about your struggles. So anyway, um, that aside, I wanted to look at a molecular modeling kit that I use to kind of help me visualize what's happening. As a suggestion, I know that Dr. Larson offers these molecular modeling kits for students to borrow and returned intact to her every semester. She's very generous to offer these to us, but of course this is my own. I ordered it off of Amazon. It's something that I use so much that I couldn't in good conscience borrow it for several semesters, so went ahead and ordered my own. But we're going to be looking at this particular representation of a diastereoselectivity and the intramolecular Diels Alder reaction, which is very similar to what was presented to us on the exam and is very similar to what was presented to us on the quiz. And also, I just wanted to say that I'm going to also offer an alternative way to look at it because it's really kind of hard to look at on paper, and you kind of have to just put your pen to paper and tinker with it a bit. But I think that having a molecular modeling kit is so valid and useful. So this is what kind of molecule we're looking at. And so for the R substitution, I just went ahead and used two CH3 groups. So the white little balls are hydrogens and the black are carbons. And you can see where I have formed double bonds here. And one thing that really helps when you're looking at this molecular modeling kit is you can see that the double bonds, they don't twist at all. They don't go anywhere, but the single bonds, they can rotate. But if you notice that rotating one single bond does not affect the other bond angles. So that's where it gets tricky when you're writing it on paper. And that's why having a molecular modeling kit and being able to write it on paper are both valid and important. At least what I found was most helpful so far for me. So looking at this intermolecular reaction, we can see that according to this PDF, it forms a cis-fused product. So we know that cis is same side from our other lectures, and we know fusion is the bringing of stuff together. So the first thing that we're going to have to do is we're going to have to rotate this bond angle here to get our diene in not a trans but an S-cis position, which is something that is intuitive, that we do know by now, right? So I did that. I went ahead and I flipped it over, and I've got two double bonds that are in S-cis position. These are my double bonds here that I'm pointing to right here. So I left the rest of the molecule as is. So we can see the kind of beginning of where the six-membered ring is going to form. I've got 1, 2, 3, 4, 5. I'm missing my sixth little carbon down here. And we know that in order to get that sixth little carbon, I'm going to get that from the dienophile, right? That's what, isn't it? Isn't that what happens? So, I don't know. Let's see. Well, no. Nope, that's not right either. See, this is why I'm talking about it. 1, 2, 3, 4. We're going to get 5 and 6 from the dienophile. I'm sorry. This carbon, this carbon, this carbon, they're going to be forming the other product, because what's going to happen is we're going to rotate again to get this dienophile closer to these products, or closer to the dienophile, so that they can split bonds and begin to form the six-membered ring. Where? Okay, so another thing is I've noticed on the molecular modeling kits, when you get to have molecules that are so big like this, they start to get kind of floppy. And so they're kind of hard to work with unless they're actually laying flat on a table. And then you can manipulate them. Unfortunately, I don't have that kind of capability to show that to you guys. So instead, looking at paper. So if you look, you can tell that I've redrawn this in a rigid nature so that you can tell where I'm rotating the bonds. I'm going to rotate here first to get our S-cis diene. Okay, so the next thing that I have to do is I need to rotate the dienophile so that it is closer to the diene without puckering or stressing the bonds so much that they break and the molecule is lost. So we want to I want to do this in a way that brings the dienophile and the diene close together, yet at the same time kind of holds true to the intramolecular forces. So I think the next most important thing to remember during this reaction is we have 3 pi bonds breaking. Now, the key to understanding the next step of how it is formed is where those pi bonds are staying attached. Not necessarily, you know that they break, but where do they stay attached and why? And it all has to do with stereochemistry of the molecule itself. Which attached position, whether up top or down low, is favored and why. And so I'll go ahead and show you the molecule that I have and where see the attachments where the bonds have been broken, but they stay attached in certain positions. So these are not floating electrons. They stay closer to the nucleus in certain positions. And the reason is because that's what's going to favor the bicyclic structure. So I'll try and draw it out and show it to you on the paper. Okay, so what I did as representative for the carbons that kept the electrons versus the ones that didn't, is if you look really close, you can see that there's little happy faces and little sad faces. And these are sad little carbons, and these are happy little carbons. And they're happy little carbons because they have 2 extra electrons. And these are sad little carbons because they have an empty place, a little hole in their little quantum heart, if you will, which you can actually see on the models. See, they've got a little hole in their heart. They're sad. They're missing something. They're not yet complete. They need something to fill them up. So what happens is then these because of these intramolecular forces, the molecule wants to reach stability. It wants to have balance in its life. It's just like anything else in the universe. It's just like you and me. We want balance. We want piece. And so that little molecule is going to go for that. And so where there's a little happy face, it's going to go to a little sad face. And it kind of goes around in this order, just like we remembered from the arrows. So let me see if I can draw that for you real quick. Okay, and so that's what I did. I took the little happy electrons on the happy little fulfilled carbon. He doesn't want his neighbor to be depressed, so he's going to travel up here, and they're going to form a marriage, if you will, between the carbons. They're going to have an unbreakable bond. We're just going to go with that. Okay. But, and then we'll see what happens. Now they're all going to be little happy carbons. Okay, I didn't want to pick the model up because I want you to see like how it actually twists and stuff on the paper. I took some photos. This is why it's really, really difficult to actually represent on paper. If you can see, this is the first image I captured. And then we have a second image where you can see the twisting rotation, and there again. And so it looks all funky, really, right? Like, because you 1, 2, 3, 4, 5, 6, and then 1, 2, 3, 4, 5. And you have to kind of be able to hold the model in your hand and twist it to see, okay, yeah, I can see that's a 5-membered ring, and yeah, I can see that's a 6-membered ring with a double bond here. So here's what I got on my paper for the representation. First, let me go ahead and switch back over to, here we go. Here we are. Okay. Sorry about that, guys. I apologize. I am struggling a little bit here with this video. This is really hard to do. Just so you guys know, I put some work into this to try and be helpful. Okay. Yeah, here we go. Okay, so what I found was that Newman projections become necessary in drawing the final product, because you can see where these two molecules overlap. So that's actually 2 carbons there. 1, 2, 3, 4, 5. And then, of course, where these two connect, 1, 2, 3, 4, 5, 6. So anyway, this is remember the R group. So this is not part of the 3-membered ring. But again, Newman projections become necessary for you to write it out on paper, for you to get a model idea of what it looks like. So that's what I found useful as far as paper modeling. And if you wanted to do an actual model using a molecule kit, you can do that. But I thought that this was very difficult and definitely not intuitive. The publication that I've been using to kind of guide me throughout this is from Princeton University. It was published back in 2001 from one of the professors there. Let me see if I can scroll up. It's called Intramolecular Diels Alder Reactions by Rebecca Wilson. And I tried to figure out a way to attach it as an attachment in this discussion forum so you guys could use it, but unfortunately, I know you all weren't able to view that, so I wasn't able to link it over. So if any of you all are interested in looking at this paper, or again looking at how I went about and did paper modeling for these reactions, feel free to shoot me an email or give me some feedback. Thanks so much. Have a great day.